Howdy, we are the Turbine Company, and this is the layout for our airborne wind turbine. The design specifications laid out for us were that we had to hover at least 30 meters above the ground and generate 100 watts of electricity. At this, we had to be able to produce electricity at a minimum wind speed of 3 meters per second and automatically yaw into the wind. This has to be safely launched and landed by 2 people and maintain a position that deviates in less than 2 meters in any direction. The cost will be approximately $5,000.
So this is the mechanical design of our design. The main components of our design consist of a connection piece, a weather vane, a mechanical equipment piece, pivot joint, pivot piece, weather balloon, rotor shaft, and rotor. The connection piece is the body of our aircraft, body of our rotorcraft, and is what actually connects everything to one another. The weather vane is what is used for the yawing. The mechanical equipment piece is what will be used to store the generator and other electronic equipment. The pivot piece and the pivot joint are a special feature on our design that will be elaborated on in the stability and characteristics part. The weather balloon is what will provide the buoyant force to lift our body, and the rotor shaft and rotor are designed such as to be there to provide thrust. The material selection for design components is as follows. The connection piece, pivot piece, mechanical equipment piece, weather vane, and pivot joint are all anticipated to be made out of lightweight aluminum alloy and be manufactured in-house, preferably out of a material commonly known as aluminum towel rod. The rotor will be made out of a lightweight carbon fiber and more than likely be manufactured in-house, but possibly can be bought off the shelf if we were able to find one that was as to our specifications. The rotor shaft will be made out of lightweight aluminum alloy, preferably one that's stronger and can endure more, and be purchased off the shelf. The weather balloon will be made of latex and be purchased off the shelf. And the assembly of our design is accomplished mainly with the use of steel nuts and bolts. The mechanical equipment piece attaches to both the weather vane and the connection piece, which is highlighted in the picture. The pivot piece attaches to the pivot joint, and the pivot joint attaches to the connection piece, which is highlighted in the second picture. The propeller attaches to the propeller shaft, and the propeller shaft to the generator as dictated by the specifications from the off-the-shelf source. The weather balloon slides over the pivot piece and is bonded with epoxy and sealed to ensure no leaks. In total, about 5 or 6 steel nuts and bolts are used as a highly efficient and cost-effective method of assembly. In the structural analysis for our design, we used the technique of virtual work. In this technique, we assume the point where the 2 tethers attach is going to be fixed. A maximum downward force of 150 newtons was applied to each of the points, and a maximum 250 newton upward force was applied to where the pivot point attaches to the connection piece. Due to this, there was a vertical deflection of approximately 2 millimeters calculated based on the virtual work technique, and a maximum stress of approximately 5 megapascals occurs along the external wall of the connection piece. As aluminum has a yield stress of 95 megapascals, we assume structural failure will not be a problem.
So for the rotor aerodynamics, we developed our own blade element momentum theory code to iteratively design our rotor. At first, our first design for our rotor was a 3-blade rotor that had an extremely high rotation rate. It was, I believe, 180 rotations per minute. This was fairly high considering the size of rotor we were looking at. We didn't want to deal with the dynamics of a rotor spinning that fast, and a lower rotation rate would help with shaft power losses. So we decided to go with a much lower rotation rate, but because of the size of our blade, we were looking at a tip-speed ratio of around 2, which is fairly low. So doing some research on wind turbine design, I found that with a tip-speed ratio of 2, a 6 to 12 blade design is most efficient, so we settled with a 6-blade design. I also found that at tip-speed ratios that low, you can use curved plates instead of airfoils, which make our rotor much easier to design. The size we ended up coming up with was 1.72 meter radius. We did a piecewise linear chord distribution, ramping up from near 0 at the hub to half a meter and then back down, tapering back down, and a linear twist distribution. Here's a picture of our rotor geometry. For our BEMT, I used the NACA 9508 to estimate a curved plate because it was the easiest thing to find data for all 360 degrees angle of attack. This is just some really preliminary power versus altitude and wind speed plots for a given height off the ground and varying wind speed, the power generated. You can see we're generating 100 watts at 30 meters above the ground and 3 meters per second ground wind speed. And that concludes rotor aerodynamics.
From a stability and control standpoint on this project, there were two things that mattered. The first was designing a controller to control our aircraft. The second was to prove that with this controller, our vehicle was statically and dynamically stable. First thing I had to do was build a mathematical model of the vehicle. Rather than simulating all 6 of the vehicle's degrees of freedom, which is time consuming both computationally and in manpower, I reduced it to 4. The most important two, inarguably, are pitch and yaw angle. If we have any misalignment with the incoming wind, we're going to see loss of efficiency. The other two I chose were altitude and distance from the tether point. You can think of that as how far downwind our vehicle has been blown from where it's tethered to the ground. I considered forces on 5 components: the rotor, vertical tail, balloon, and the 2 tethers. One tether is forward of the CG and the other is aft. This gives us pitching authority just by varying the tension on the tethers. The controller was multiple input, multiple output. We had 2 outputs, so we can control 2 degrees of freedom effectively. I chose to control altitude and pitch. Each degree of freedom had its own PID controller. The altitude controller controlled the tension in both of the tethers, so if we want to go up, decrease the overall tension. If we want to go down, vice versa. The other PID controller controlled the pitch. It set differential tension in the line. So to decrease pitch, we would increase tension in the foremost tether and decrease it in the aftmost. The controller was calibrated experimentally through the simulation to give an overdamped response, which is what you want for a wind turbine. This chart here is a 100-second simulation of our wind turbine. All variables are steady state except for the wind heading angle, which shifts 10 degrees to the right at t equals 10 seconds. You can see on the top graph, the red dashed line is our vehicle slowly turning into this 10-degree change in wind. We have about a 90-second response time, which is what we anticipate you want for a wind turbine. And we have sized our vertical tail to give us this response. This graph is very similar, except rather than the wind heading changing, the wind speed increases 1 meter a second at 10 seconds again. So the pitch is affected slightly, but not a whole bunch. The altitude controller keeps the altitude within our 2 meters from the set point as required by the RFP, and the vehicle is, as expected, blown downwind by this. Now, you may have noticed a hinge was introduced in the vehicle design, and this serves to decouple the drag on the balloon from the pitching moment. Right now we have a large buff body attached on a very long arm to our vehicle. So if this pitching moment wasn't in there and we had a change in wind velocity, that would increase the drag. We've got a long moment arm, so we have a lot of pitching moments. So we put the hinge in there so the balloon balances its lift drag and contributes almost no pitching moment to the vehicle. Just doing some rough calculations, we're anticipating a deviation of 15 degrees from vertical, so there shouldn't be a huge deal with vehicle dynamics. And we're thinking about putting mechanical limiters on this hinge so that the balloon cannot flap forward and hit the rotor or flap back too far.
Final part of the project was choosing a generator and then analyzing what kind of losses that we're going to encounter with the alternator that we choose. We've chosen the WindBlue Power DC540 low wind permanent magnet alternator. It's ideal for wind speeds from 3 to 10 meters per second based on manufacturer testing, and it's capable of generating 100 watts at about 225 RPMs on the shaft. Now, we're obviously, since our rotor is going to be operating at low RPMs, we're going to have some sort of a gearing system which enables the shaft to spin at higher rates than the actual rotors themselves. So here's an example. If you have a 3-to-1 gear ratio, you can actually get by with only having 75 RPM on the rotors and still maintaining 225 RPM on the shaft, and so on with different gear ratios. There's going to have to be some testing that goes on to see which kind of gear ratio is the most effective, and more complex scenarios can be implemented to make this RPM the ultimate value. This is an example of the power output based on the manufacturer's testing. The main thing to take away here is the dashed blue line, which shows that at the 225 RPM of the shaft, we can generate 100 watts of electricity. So once we chose the generator, we needed to analyze what the losses are going to be and what kind of efficiency that we're looking at it from a power standpoint. We did this 3 different ways. First, we compared what our blade element momentum theory calculations output were compared to the ideal wind power from the incoming velocity. Then we compared the power generated at that RPM level and compared that to the BEMT code. And then last, we calculated what kind of losses we're going to have while transmitting the electricity from the system, which is suspended in the air, to the ground. Okay, as you can see here, the BEMT power output at 3.6 meters per second is just right around 100 watts. The ideal wind power at that velocity is about 259 watts. So you can see that our power coefficient ideally is about 0.39. Now the BET's maximum theoretical limit is about 0.59 for wind turbines. So this 0.39 number is actually a fairly good result considering what the maximum limit is. Secondly, we compared the BEMT output and to the power generated by the motor itself at the RPM that we're operating at. Again, the BEMT power output at that velocity is 101 watts. If we implement a 5-to-1 gear ratio, we can generate about 95 watts of power, giving us a 94% effective generator. Okay, last we needed to calculate the transmission efficiency through the wiring all the way to the ground. Basic 12-gauge wiring has resistance of about 0.0016 ohms per foot. We've got approximately 150 feet of transmission wiring from the system suspended in the air all the way to the ground. After you do some math, you can find that we lose about 6 watts of power if we're generating 100 watts from the generator. So that gives us about 94% efficiency through the wiring. So overall, if you multiply all those 3 factors together, you find that the power coefficient is about 0.36. And again, considering that that the maximum efficiency is about 0.59 and that our code actually accounts for tip losses, this is a significant result. So finally, for the cost analysis, you can see in this chart that we've broken down the components of the system into hardware, the balloon, the generator, and other things. The most notable ones are the generator. It's only $329, which is fairly inexpensive for a generator for what we're doing. The rotor blades themselves, we estimated that they would be about $125 a blade. Now this is if we were to not buy off-the-shelf blades. There are blades that could be considered flat plates or curved plates that can be bought off the shelf for a significantly cheaper cost. So our price point can be driven down by doing that. Lastly, helium is pretty expensive. It's roughly $1.50 plus per cubic foot, and we're going to need about 600 cubic feet to initially inflate the balloon. It's going to run about $900. So the actual system itself is going to be right at our $5,000 price point. Once you inflate the balloon, it's actually going to be a little bit above that. These predictions don't include maintenance costs, life cycle costs, and such, so those would need to be considered if this design actually does make it to the next phase of being built. And lastly, like I said, you can decrease the cost by purchasing off-the-shelf rotor blades and also by having a simple ground actuation system. And finally, launch and recovery. This is a pretty simple process. Basically how it's going to work is that the ground tethers are going to initially be at the 0 position. The balloon's then going to inflate slowly through the plastic tubing until the upward buoyant force exceeds the weight of the entire system. At that point, the ground control system is going to regulate the position and the height of the design. Once it's at its operating height, the system will automatically orient itself into the wind just based on aerodynamics alone. Recovery is basically the exact opposite process. Helium is going to slowly be taken out of the balloon as the tethers are retracted into their housings until the system slowly touches the ground. And during this whole process, the helium is going to be compressed on the ground so that we can restore it for future use. That way, we're not wasting money.
That concludes the specifications for our airborne wind turbine design. Thank you for the opportunity to participate in this project. Thanks, and gig 'em.